In this chapter 6, which is the second one about experiments, you will learn a little bit more about experiment designs. In chapter 5, we have learned about one-track experiments, which are not really well designed, and about randomized comparative experiments, in which all the subjects are allocated at random among the groups, among experimental groups and control groups. But there are more. There is not only this experiment design. We will learn more here. For example, a block design is another experiment design in which, before assigning subjects at random between experimental and control groups, we separate them according to a variable that could become a lurking variable in research. For example, I could separate men and women into different categories before assigning each man and each woman into different groups. I will show you a diagram so you will understand block design better. But before seeing a diagram for a block design, I will remind you what is a randomized comparative design. For example, if I have the following research question: to what extent drinking alcohol affects driving abilities? That's an interesting research question, and I could answer that question by doing a randomized comparative experiment, the type of experiment you have learned in chapter 5. It would look like this. I have 100 subjects for that experiment. So I would randomly assign them into two different groups. My first group of 50 subjects will receive a treatment. They would drink 3 beers here. And my second group, composed of 50 similar subjects, would receive a placebo. They would drink 3 beers, but without any alcohol content. So here I have my experimental group, group 1, and my control group receiving the placebo, group 2. After that, I would ask them to drive a car in a parking lot somewhere where it's safe, and I would compare their driving abilities. So if group 1, those who drink beer, drive very badly, and those in group 2 without alcohol drive very well, I would assume that there is an important difference between groups, and I would assume there is statistical significance here. Alcohol affects driving abilities. That would be a randomized comparative experiment. But I suspect there is a lurking variable around. I suspect that gender might be a lurking variable. I suspect that alcohol will affect men and women differently. So here, instead of designing a very simple randomized comparative experiment, I would do what I call a block design. I will first take my 100 initial subject and I will separate men and women. And I would do kind of 2 twin experiments, one with men and one separate one with women. So let's assume I have 50 women and 50 men in my initial 100 subjects. So here you see, you have a randomized comparative experiment up the line with men and down below the line with women. So my 50 men, I will randomly assign men into 2 groups, one experimental group and one control group. The experimental group will drink beers, and the control group will drink non-alcoholic beers. And then I will compare men with men. I will do the exact same thing with women. So I will compare women who drink beer and women who do not drink beer. So here, if initially gender was a lurking variable, by doing a block design, by using gender as my blocking variable, I can eliminate that source of bias because I separately compare men and women. In order to eliminate as many lurking variables as possible, I could do what I call a matched pairs design. In such a design, I place my subjects into pairs. So I place them 2 by 2, and each pair of subjects includes 2 subjects as similar as possible. So in my original subjects, let's say I take the same experiment, does alcohol affect driving abilities? I will use pairs of very similar subjects. For example, I will take in one pair 2 men, 25 years old, 180 pounds. This is a very similar pair. We'll have another pair of 2 women, 30 years old, 160 pounds. So I will have a group of pairs like that. So they're very similar. So here I eliminate not only gender as a lurking variable, but I eliminate age, and weight, because weight can affect how you process alcohol. I can eliminate all sorts of variables here, lurking variables. I can place them with I can take into consideration their health status, their height, etc. This is called a matched pairs design. Subjects are grouped into pairs of 2 subjects which are very, very similar. Sometimes each so-called pair could consist of only 1 subject. In this case, you're very sure your 2 subjects in your pair are similar. It's the same person. This person will get both treatments, but one after the other. For example, for my same question, does drinking beer affect driving abilities? I will take many subjects, but I will take one by one. The first day, I give a subject 3 beers, and I ask the subject to drive around cones in a parking lot. 2 days after, I ask the same subject to do the same activity without drinking beer. So in this case, I will have very accurate results. This is a diagram showing how we do a matched pair design. We group subject in 2 pairs, and one subject of the pair receives the treatment and one subject of the pair receives the placebo. And with who receives the treatment, who receives the placebo is determined by random assignment. Experiments are ideally what we call double blind. It means the subject do not know if they are in the experimental group or in the control group. And people who work directly with them don't know either. So if I do that beer and driving experiment, I don't know if I receive the real beers or the non-alcoholic beers, which are placebo. So I don't suffer from the placebo effect, because if I know I'm receiving the real treatment, I might be subject to the placebo effect. I may feel more drunk because I know I'm drinking beer, for example. Even if an experiment is very well designed, either with random assignment or by a block design, a matched pairs design, even if it's well done, double blind, there always are possible sources of bias. For example, some subjects might refuse to participate in an experiment. Example, I have to disclose the nature of my experiment before I ask subject to participate. This is an ethical consideration here. Suppose I want to do an experiment about how extreme stress will affect cognitive abilities. So I would have to ask subjects to undergo some stress. Maybe some people don't like to be stressed. So maybe people who are anxious or nervous will refuse to participate in my experiment. So in my sample of subjects, I will not have the diversity I would like to have. I would have only people with good confidence in themselves. So refusal to participate is a possible source of bias. Also, some people sometimes will drop out. They will start the experiment and then they will say, I don't like it, it's too long, it's too hard, I just leave. So they drop out, and this will also lead to a lack of diversity in my sample. Not good. Sometimes experiments take many years to conduct. You give a treatment to a series of subjects at one time, and then 1 year after they're older, you give them the same treatment. It's a long process, and sometimes people got disinterested. Also, some people do participate, they accept, and they don't drop out, they do it until the end, but they don't do it well. We call them non-adherers. They don't follow the treatment, they don't follow the rules well. So this will bring a bias in my experiment. If, for example, I have an experiment about studying and memory. So I'm asking subjects to spend 1 hour into a room and study something. And after that, they will have to memorize and recall. And subjects are tired of studying after 15 minutes. So they just do something else. Well, they participate into the experiment, but they don't follow the procedure well. So this will bring bias in the results. So even if there is a good experiment design, there are always sources of bias to consider in experiments.